amplitude. And what I have sketched here is, hopefully you realize, is the sine function, y equals sine x. And I have approximately one period graphed here from 0 to 2 pi. And again, it is the parent function of y equals sine x. And today we're going to talk about amplitude. So I'm going to slide to the right here and build off of some previous knowledge that you have regarding, again, the parabola. It's just something you've worked with numerous times, and so it's kind of an easy target. So here we go. We have the x and y axis, and I'm going to graph y equals x squared, which is the parent function of the parabola. We'll leave it in blue. And so it looks something, again, like this. And again, not to scale. And if I use the vertex form of the parabola, and I'm going to focus in on this a part. So I'm just going to deal with this. A, x, oops, I don't want that stuff. Ax squared. So everything is the same between these portions of our functions. The only thing that's different is this a. And so let's give an example. Y equals 7x squared. So previously, if I put a 0 in for x, I would get 0 squared, which is 0. And so I get that little point on the origin. The vertex is on the origin. In this one, we kind of get the same thing. Not kind of, we absolutely get the same thing. 7 times 0 squared equals 7 times 0, which is 0. And so we still get this point right here. But note what happens when I use values other than 0. And so if I put 1 in here, I get 1 squared, which is 1. So at 1, I get 1, something like that. And again, scale's not exactly perfect or correct. But for this function down here, I'll get 7 times 1 squared, which is 7 times 1, which is 7. So up until this point, until I multiply times this 7, I get the same value. But in this case, I get 1 and 7. So it's already shooting off of the screen above what I have drawn here. And if I put negative 1 in there, I'm going to get negative 1 squared times 7, which is 7 times 1, again, same value. So over here at negative 1, I'm shooting off the screen again. So if you've had me previously, if you heard me talk before, I think of this a value as dictating how quickly or how slowly I go up or down the y-axis. If that a value is greater than 1, if that a value is greater than 1 or less than negative 1, my parabola gets skinnier, or as I say, it makes me shoot up the y-axis way faster. Or if it's negative, it'll go down the y-axis a lot faster. And in the same way, our sine and cosine, our periodic functions, work in the exact same way. But before I jump over there, I want to make sure I point out what happens if my a value is less than 1 but greater than 0. So for instance, if I have, I don't want to use that color. Let's use orange. And that's not what I wanted, but that'll work. Y equals 1/2 x squared. If I put 0 in there, I still get this vertex point. So it doesn't change the location of my parabola. It only changes what it looks like. And so when I put 1 in, I'll get 1 squared, which is 1. But then I'll multiply it times 1/2. And instead of getting that value, I get this value. And if I put negative 1, again, negative 1 squared is 1. I get this value. And what's happening is it's flattening out my parabola or making it wider than the parent function, which is the blue one. So values that are less than 1 but greater than 0 will compress or flatten out my parabola or make it wider. And the same, again, like I said, the same thing happens over here with our trigonometric functions. So let me erase this word amplitude because it's gigantic and taking up space. And since this green function is my parent function, I'll change the colors here. Y equals sine x, and we'll go with I don't know, hot pink, and we're going to go y equals let's say 2 sine x. So again, this part functions in the exact same way as this part. So I would get the same thing. I would get this same trace in hot pink as I do in the lime green. But because of this multiplier, this 2, all of these values are going to be twice as much. So this 0 will be 0 times 2, which is 0. But this value will be 2 times as much, so it'll be, looks like it's going to be around there. And this 1, right, 1 will be 2. It'll be up there. And so what ends up happening is I get this going on with my sine function. And in contrast, if I have an a value or amplitude that is less than 1, I'm going to use 1/2 again just because the math is easy. This part stays the same. I get the same values. I get those green values, but they're all cut in half. So I end up getting this sort of compression, vertical compression of my sine curve. So it flattens out. And so that squishing or stretching, vertical stretching or vertical compression is amplitude. Now there's something else you need to know. When I'm talking about amplitude, amplitude is always positive. Always positive is always, that's always, positive, which means that the idea of amplitude of any of these trigonometric functions is equal to the absolute value of whatever that number is in the front. And when I say front, it's the coefficient on the trig function. The problems we have, they'll arrange the vertical translation term, they'll put it up front. They'll provide you things like this: 7 plus 8 sine x. And they're going to ask you what the amplitude is, and I've seen too many students say the amplitude is equal to 7. Well, it's not. It's equal to 8. It's the coefficient of the trig function, not just the first number that comes after the equal sign. And again, if I have this function, y equals -3 sine x, well, this 3 tells me that it's an amplitude of absolute value of -3, which is 3. So I have an amplitude of 3. Again, that's taking my parent function that looks something like this and turning it into something like this, right? Where it's, instead of being from -1 to 1, I'm going from -3 to 3. But this negative sign right here is going to cause something different. All of my positive values previously, all these guys up here, they're going to end up being negative. So what ends up happening with this amplitude of 3, but the coefficient of -3, it takes all these positive values and makes them negative. So they're now down here, and all the negative values positive. And so my sine curve not only stretches vertically, but it reflects about the x-axis, or as many students say, it flips. So all these positive values become negative, and all these negative values become positive, and they're further away from the midline, which is, in this case, the x-axis. Now it works the same way in our cosecant, secant, cotangent, tangent functions. It would just look a little different. For instance, if my cosecant function looks something like that, if I had an amplitude y equals 7 cosecant x, then instead of these little bumps occurring at 1 and -1, they would occur at 7 and -7. So we would just, instead of stretching, these would just get further apart. The gap between these in the parent function is 2 plus 1 and -1 from 0. But in this function, that gap would be 14 units. Okay? And the U-shaped things get stretched out as well, but that's harder to see in my opinion. Okay? And then tangent, sort of in a quick fashion. Tangent would do this. I told you anchor points for tangent, and so tangent looks sort of like this, and has these asymptotes that occur at negative pi over 2 and pi over 2. And I told you these anchor points, again, change color so it's easier to see, 0, 0, and pi over 4, 1. And there's another one over here that you could identify at negative pi over 4, -1. But you really only need 2. Or if you needed to plot those, you're not going to. You have to choose them. So if you're somebody outside of my students that you have to plot this, you're going to want to plot those 3 points and the asymptotes. But if I had y equals 3 tangent x, then instead of this value that I'm boxing with white, instead of this value being 1, it would be 3 times that 1. So your anchor point, this guy, would end up being at pi over 4, 3. Because we're just multiplying every single one of these orange points by the value of 3. So hopefully that's helpful with regard to amplitude. Remember, a negative amplitude will reflect about the x-axis,